Now let's talk about our next topic on quantile function and quantile based estimators. So in statistics and finance, quantile function is widely used. It is considered to be the inverse of a CDF function. So basically a CDF function gives us the probability that a random variable will be less than or equal to some value of x. So basically, if we recall the example that we discussed earlier of the rolling of a dice, so we had 6 options, 1, 2, 3, 4, 5, 6, and the probabilities or the CDF that were assigned were 16.6%, 33.3%, around 50%, 66.64%, 83.3%, and then 100%. So basically here we are saying that if we are interested in knowing the probability of x less than equal to 3, we would be taking this value that the probability of a dice rolling and having a value of 3 or less would be equal to 50%. So this is what we do for CDF. For the quantile, it would be opposite. So for the quantile, we would be telling that if the quantile is 50%, or what we refer as quantile 2, the value of the dice would be 3. So basically we are saying that to be able to achieve quartile 2, or what we also refer as median, the value that would be related or that would be linked to that median or quartile 2 would be 3. So basically we divide our distribution into 4 broad quantiles. Number 1 is quantile 1, which is Q1. It gives us a value of 25%. Then quantile 2 is 50%. Quantile 3 is 75%, and quantile 4 is 100%. So basically it's showing that if you're having a value of, let's say, 5, 9, 13, 17, then if you have to be in the upper quantile, you will have to score somewhere around here. Or it can also be taken in percentage. So Q1 is basically 25%, then 50%, 75%, and 100%. So basically the median or the middle function or the middle quantile that we have is 0.5. Now quartile 1 is referred as lower quartile and quartile 3 is considered as upper quartile. So basically here we are saying that for the lower quartile, Px less than 1 is equal to 0.25, while for the upper quartile, the Px less than 3 is equal to 0.75 or 75%. Now the lower value of 25% infers that we expect 25% of the outcomes to be less than that particular value. And on the other hand, the upper value is the value that we expect 75% values to be less than that particular value. Then we have another concept of interquartile range. Now interquartile range is actually calculated using the differential of quartile 3 and quartile 1. So it basically gives us the dispersion of the equation. So here we have quartile 1, here we have median or quartile 2, here we have quartile 3, and here we have quartile 4. So basically this particular portion, which is quartile 3 minus quartile 1, gives us the idea about the distribution, that how many values are there which lies between these two quarters. It also includes the middle or the median of the distribution as well. Another extension of the quantile function is percentile. So to be able to calculate percentile, we actually calculate percentages. So the first percentile is 10%, the second percentile is 10%, and so on and so forth. Both quartiles and percentiles are used in a lot of application. Interesting enough, the FRM certification also gives you a result in terms of quartiles. Now let's discuss the concept of mode. As we discussed earlier, there are three major concepts. The number one is mean, number two is median, number three is mode. So whatever we study today in this particular chapter is just more of an introduction. We'll be talking about mean, median, mode in more detail in the coming chapters. So basically the mode measures the common tendency, that is the location of the most observed value of a random variable. So if we have a distribution x in which the value of 2, 3, 3, 5, 3, 4, 3, 5. Here we have 1, 2, 3, 4. So we have 4 threes, which is the most common value in this particular series. So the mode of this series would be 3. So whenever, if we'll be plotting this particular graph, we will having 3 here. So the mode would always be the topmost value or topmost histogram for the distribution. Or we can also say that mode is actually represented by the highest point in the PDF. There are two concepts where there can be a unimodal or there can be a bimodal distribution. So this sort of normal distribution is an example of a unimode or unimodal where we have only one mode available in the distribution. But let's suppose that we had also 7 here in this particular distribution. So in this particular case, if we have two modes, we can have a bimodal distribution, which would look like something like this. So basically there are two modes which are most numbers. So there are 4 3s and there are 4 7 as well. And then we can have multi-modal distribution as well, where we have more than 2 modes in the distribution. In the last, let's discuss how linear transformation can affect movement. So before we discuss how linear transformation can affect movement, let's recall what linear transformation is. So we had a variable x and we can have a value or a variable known as y. So the GDP can be considered as y and inflation can be considered as x. Now we can use linear transformation in order to make a relation of these two factors. So we can write y is equal to a plus bx. This is what we can refer as a simple regression equation or what we refer as linear transformation. So if we want to establish a linear relationship between y and x, it can be developed through this particular example or through this particular equation. So basically in the statistics and probability, transformation plays a significant role. So we have a linear transformation, we have an inverse transformation, we have a log transformation. We do these sort of transformations to make our data valid or what we can refer as comparable to each other. So in this particular linear transformation, the constant a actually shifts the location of the variable. So if a is equal to 2, whatever the value of this factor is, it will be shifted by 2. And the b actually rescales the impact of variable x. So if b is equal to 1, there will be any impact, but if b is equal to 10, it will have a huge impact or a huge scaling impact on the size of the x. Now, if we talk about what impact can we have of these linear transformation on our moments, if we calculate mean of y in this particular equation, we can see that expected y would be equal to a. So a would be a constant, so its value would remain the same. The b will also come out and this expected s will be calculated separately. So both the location and the scale would be taken out and the expected x would be measuring the impact of expected y. Similarly, if we have variance of y, so basically in the case of linear transformation, the sigma square y would be equal to b square into sigma square x. So while a shift in the location of the distribution, it does not affect the dispersion around the mean, which is rescaled by b. So there will be some change, but it will just be the rescaling. Similarly, the standard deviation of y, or what we refer as sigma y, would be equal to square root of sigma square into b square, and it will be equal to b into sigma y. In this particular case, the b will have the similar impact, so there wouldn't be any significant impact on the standard deviation of the factor based on linear transformation. Then if we talk about skewness, there are two cases. If b is positive, which is an increasing transformation, so here the b is actually positive, the skew is not effective, and skew y would remain equal to skew of x, so there is any change as such. But if it is decreasing, if it is y is equal to a minus bx, then the magnitude of the skew remains the same, but the sign would change. So the skew y would become equal to negative of skew x. So everything would remain same, but the distribution would become negative. So if we put it like this, it will move to this, so it will change its sign. And in the end, a linear transformation of x does not affect kurtosis, and kurtosis of y would still remain equal to kurtosis of x. So this is what we had from this chapter. Thank you.